Hello and welcome, Bhaskar this side. So in today's session we will talk about the basics of peak purity, followed by what are the three important critical parameters that we need to decide during the measurement of the peak purity. I mean, the peak purity is one of the very important concept but which is highly misunderstood. So first let us understand what is really mean by the peak purity. So once you run the chromatogram by using a detector like photodiode array, you are acquiring the information not only about the absorbance but also about the spectra. So once you gather the information from start to end of the chromatogram for any specific peak, then you can actually conduct the peak purity. So what is the definition of peak purity? And here it is onto the screen. So peak purity is a spectral homogeneity across a peak. In a given example, I have given the three different spectras. One spectra belongs to the at the beginning of the peak. The second spectra belongs to the apex, and the last spectra belongs to the tailing of the peak. Now, if these three peaks are homogeneous, I mean if they are similar in their structure, then we can say that my peak is pure. Alternatively, the peak purity is nothing but the evaluation of sameness of the UV spectra across a peak. How the peak are similar, and according to that we can confirm whether the peak is pure or peak is not pure. So what is the purpose of measuring peak purity? The peak purity helps us in understanding whether there is a possibility of co-elution. In case if the peak is spectrally pure, that indicates that all the spectras present into a peak belong to a one and the same compound, and hence there is absence of another compound or the co-elution. Or in case if there is a impure peak purity observed, that in case if the peak purity is not pure, that also indicates that there must be something co-eluting along with the peak. So peak purity is not a chemical purity, which is a very important point that I would like to reiterate over here. Now let us understand what is the general process of evaluation of the peak purity. So to evaluate the peak purity, you need to run a sample by using photodiode array detector and record the spectra across the entire chromatogram from start to end. Then second point is once you have the chromatogram run, you can extract the chromatograms across the peak. The way I shown the three spectras at the beginning, at the apex and at the end. So I have extracted the UV spectras across the peak. Then you need to normalize the UV spectra, and I will talk about the normalization process in the few next slides. Once you normalize all the UV spectra across the peak, then you can overlay them to compare and understand whether they are similar or homogeneous. Let us take an example to explain this process further. So there are two peaks in the given chromatogram, and if you look at the first peak which belongs to folic acid, now this is the spectra across the peak. Now, do you think that these peaks are, do you think that these UV spectra are homogeneous? It looks to be not homogeneous, right? So what this indicates, if these UV spectra are not homogeneous, there may be possibility of multiple components under the given peak. So whatever you are, getting a peak at folic acid may not be only folic acid, but there must be something co-eluting along with that. Why? Because the spectra are not homogeneous. Let us look at the second peak. And what do you think about the second peak? Is it homogeneous or not homogeneous? It is looks to be a very homogeneous, and that indicates that the chances are there is no component other than the methotrexate, right? So that is the only component likely to be present in the second peak because the peak is homogeneous. So with the help of the spectra across the peak, we can able to determine whether there is a possibility of coevolution or there is no possibility of co-illusion. Let us understand now what is meant by the UV spectra normalization. So once you run a chromatogram, the one that you are now seeing onto the screen, you are going to map the absorbance values from the start of the peak, apex, and the end of the peak. So what do you think about the absorbance at the apex as compared to the absorbance at the beginning or at the end of the peak? Absolutely, it is the highest one. And the absorbance across the uh, peak, like at the beginning and at the end, is going to be very minimum. And if I extract the UV spectra out of the apex, and let us say from the point where the peak is just about to end, the absorbance value is very much higher for the apex spectra, and that looks with the greater absorbance value or the height. Similarly, the UV spectra for the tailing of the peak is having very minimum absorbance value, and that can be denoted by the blue colored spectra. Now the point over here is we are going to compare the UV spectra. But how one can compare the UV spectra with the higher magnitude and with the smaller magnitude? It may not be possible to compare accurately, and for that reason there comes a process which normalizes the spectra. In simple manner, you are going to make the similar scale. You are going to make both the spectra into a similar scale, and after normalization, this both the spectra will look like this. Okay, so in short, normalization is a simple technique used for comparison. I hope you understand the normalization technique. Now, what are the three important parameters that I am going to explain you throughout this presentation, and which are very important as far as evaluation of peak purity is concerned? The parameter number one is the wavelength, second one is resolution, and the third one is the sampling rate. So this entire presentation is going to be built on the basis of Empower software. I'm going to explain these parameters based on to the Empower software. So the first parameter is now the wavelength. So what is the role of wavelength? If you look onto the screen, you will find that the default wavelength is, for example, 210 nanometer to 400 nanometer. So is it the right wavelength, or do you need to change the wavelength? Let us get this answer right away. And here is the answer for that. The wavelength range should start above the UV cutoff of the mobile phase and end in the region that includes the absorbance for peaks of interest. I will explain you with the help of example. Now, once you collect the data, let us say you have a detector setting from 200 nanometer to 400 nanometer. It's okay to collect the data from such a wider range, but upon collection of the data, you need to process that with the smaller wavelength range of your interest. So please allow me to explain you with the very simple example. So onto the screen, you are finding a UV spectra of isoprene, which is having the lambda max of 222 nanometer. Now, if you look at the first point, it talks about the UV cutoff of the mobile phase. So why the mobile phase will have the UV cutoff? Because of the organic solvent or the salt present inside it. Let us assume that for this example, our mobile phase UV cutoff is only 200 nanometer. That means you will get the absorbance value of around zero point 0.5 AU at 200 nanometer. Now, what is the detection wavelength for this particular method? It's 222 nanometer. So you are going to collect the wavelength from the range of 200 nanometer to 400 nanometer. Now this is your wavelength collection range. This is not your wavelength verification range, right? Now what is your wavelength processing range now? Once you have this information in the hand, you are going to look at the UV cutoff. You are also going to look at the what is the UV spectra and until which wavelength there is a possibility of the absorbance. Now if you look at here, now the spectra ends up at around 260 nanometer, and if I possibly say that from 280 nanometer onwards there is nothing to be really discussed. So the one end of the range I can say that around 280 nanometer, because beyond that there is nothing really to investigate. Now, what is about the lower end, whether 200 nanometer? Now, let us understand what is the UV cutoff of our mobile phase. That is 200 nanometer. That indicates that our lower wavelength should not be below 200 nanometer. So I can say that rather than 200, little above that. So the 205 nanometer looks to be good. So I will start from scanning of my spectra from 205 nanometer until 280 nanometer. I hope you understand the collection wavelength range and the processing wavelength range. The another important point is, why the wavelength range should start above the UV cutoff of the mobile phase. Now there is certain reason for that. See, in HPLC system, once you make any injection, your HPLC system does the auto zero automatically. So whatever response that you supposed to get from the mobile phase will get corrected to the zero absorbance unit value. So no characteristics absorbance or spectra can be seen below the absorbance of mobile phase. So if the UV cutoff or in case if you make the auto zero beyond that or below that wavelength, your system will not recognize any absorbance or the UV spectra. Hence, there is no point in recording the UV spectra at the lower end beyond mobile phase absorbance. So we discuss both the ends now, the higher end of the wavelength as well as the lower end of the wavelength. The second important factor is the resolution. So here is the screen of the Empower software, and the resolution can be given in the range of 1.2 nanometer. So what should be the exact resolution? But before that, let us understand what is meant by resolution. And here is the definition. So resolution is nothing but the distance between 2 points on the spectrum. So if you look any spectrum, it is actually plotted by connecting the dots across the spectra. Now what is the distance between two different adjacent dot here? That is called as the resolution. So if the difference between two adjacent dot on the spectra is 1.2 nanometer, then you can say that okay, the resolution is 1.2 nanometer between these two adjacent dot. The recommended resolution as per as Empower is concerned is 1.2 nanometer. Selecting any of the other choices will result in diode bunching or averaging. And I am going to explain you this particular phenomenon with the suitable example. Now here is the example onto your screen. So if you scan the benzene and if you select 1.2 nanometer as a resolution, you will see the spectra which is highlighted into the red line. But if you measure the similar spectra by using 4.8 nanometer, you will see the spectra in the black colored line. So what is the difference in between these two spectra? You can notice. In this example, you will see that there is a loss of some of the spectral shape for the 4.8 nanometer, whereas those spectral information is very much visible in the 1.2 nanometer. You will also see a small amount of lambda max shift with the 4.8 nanometer. So for that reason, the recommended resolution in case of Empower software is 1.2 nanometer. The third important point is the sampling rate. So what is mean by sampling rate? And let us look at the options available into the Empower. You can give the sampling rate from 1 to 80. So the definition of sampling rate is here. The number of spectra recorded per second. For example, if the 5 spectra gets recorded per second, then you can say that I have the sampling rate of 5 points per second because 5 spectra are getting recorded per second. The sampling rate should be set to yield a minimum of 12 spectra across a chromatographic peak. Now this is very important information. And why there is necessity of the 12 spectra across the peak? And here is the information. Empower need minimum 12 number of spectra to calculate the peak purity. This is a very much need of the Empower, and hence you need to have a minimum number of 12 different UV spectra across the given peak. And we are going to then connect this information with the sampling rate. So as far as HPLC analysis is concerned, where the peaks are relatively wide, right? And hence the base of the peak is going to be much larger. For that reason, a sampling rate of 1 to 2 suffice the requirement because that will collect the sufficient number of spectra. In case of UPLC, as the peaks are very sharp and the base of the peak is very thin minimum, probably you need to have some faster sampling rate such as 5 or 10 points per second. Let me also show you the calculation of the sampling rate with the help of simple example. So how many spectra will be recorded for a peak width at base of 1 minute with sampling rate of 5? So for every 1 second, so 5 spectra will get recorded because our sampling rate is 5. Now what is our base of the peak? It is 1 minute or 60 seconds. So obviously there are going to be 300, sorry, not 600, but 300 UV spectra available across this given peak. You can alternatively also able to calculate in case if you want to have only 12 UV spectra, what should be the sampling rate you must keep. But this is more than enough, right? Even the 5 spectra, the 5 sampling rate will give the 300, or if you keep the 1 as a sampling rate, you divided it by 5, it comes to around 60 spectra. But another important point over here is if you increase the sampling rate too much, your noise level of the background increase. Your response will remain same, but the noise level will get increased. For that reason, there must be a adjustment understanding that how much should be the sampling rate. Now I talked about the noise observation in case of very high sampling rate. Now what happens in case if your sampling rate is too low, you will not have a sufficient point to draw a peak. So too low sampling rate as well as too high sampling rate is a not suitable situation, but you need to have the optimized sampling rate. And I have given the example what is meant by the optimum sampling rate. At least you should have a minimum of 12 spectra across a peak. Okay, so what is the relationship between peak absorbance and the peak purity? We often notice people saying that the response of the peak should be less than 1 absorbance unit to suitably measure the peak purity. Let us now understand what is the reason for that. Empower says that keep the absorbance of all the peaks less than 1 AU. The reason is at high absorbance, a combination of effects can produce slight departure from Bayer's law because of photometric error. At higher absorbance, at higher concentration, you may not have the proportionate increase into the response value as to that of the concentration because of the photometric error. Although this error at this level have a negligible effect on quantitation, they can be a source of spectral inhomogeneity and result in distortion of spectra at the peak apex. So the major concern is your your spectra at the apex of the peak is always referred taken as the reference UV spectra to compare against the another spectra across the peak. The problem is because of the saturation of the response above 1 AU, the characteristics of the peak apex spectra itself will get changed. So there may be a uh, complete error in calculation of the peak purity. So you must look into the peak height. Now here is an example where the caffeine solution was injected at varied concentration to achieve the response from up to 3 AU. So can you see the UV spectras? Now these are all UV spectras of the caffeine. The UV spectras are quite okay with the lower concentration, but as the concentration gets increased, the response also gets increased. And if you look at the top spectra over here, it is actually plateaued, got saturated. And if you normalize this UV spectras, then you can see that these UV spectras are not looks to be homogeneous. There is an evidence of non-linearity, and this is purely because of not that there is some correlating peak available in the chromatogram, but because of the peak height more than 1 AU. So let me show you. Once you reduce the concentration of the caffeine solution, and then these are the injections made where the peak height is only up to 1 AU but not beyond that. Would you like to see the normalized UV spectra? And they are shared onto the screen. So you can say that there is a complete homogeneity of the normalized UV spectra when the response is lesser than 1 AU. So you must now take care of whenever there is a higher response for your, let us say, principal peak, you can dilute this solution to achieve the response below 1 AU and then measure the peak purity. Okay, so I hope now you must have understand what are the three critical parameters of the peak purity measurement, how the peak purity measurement take place, and what is the role of peak purity into your analysis. Thank you so much for watching this video, and I will meet you soon with such kind of another very informative and useful video. Bye bye.